Alright guys, so today we're going to talk about exponential growth. You might have, the name and how to identify exponential growth is literally in the name itself. So if you have an equation, basically we're looking for equations in which we have x listed as an exponent here. So in this case, 2 to the x power. So um, yes, so what we're going to look for is anytime that we have x as the exponent, that's going to represent an exponential growth. And how do we actually recognize that? So what we want to see is in a table. Let's say we had a table of values. 0, 2, 3. Okay. If our x values are these and our y values are -1, -3, -9, and -27. So we want to see every time we add 1 to our x value, do we have a common ratio between these? So this one you're going to multiply by 3, multiply by 3, multiply by 3. So what we would get is negative. So it would be -1 times 3 to the x power, right? So it'd be negative 3x. Because here we always want it to be negative, right? So 3 squared would be, if it was just 3 to the x power, that would actually equal 9, not -9 like we have here. So therefore, we know that this is an exponential equation because we got that common ratio of 3. Now, common or exponential growths and exponential decays are going to, when we graph them, they're going to basically have two different shapes. So we are going to have two different graphs here. I'm just going to show you very quickly what they'll look like. Okay, an exponential growth is going to start off low and it's going to increase incredibly fast. So it's going to start off with a pretty low slope, pretty mild slope, and it's going to increase very fast. A exponential decay is going to be the opposite. It's going to be decreasing fast and then going to slowly start, the slope is going to get more and more horizontal. So that's an exponential. This one is exponential growth. This is exponential decay. Now, let's just go through a couple. So if I wanted to figure out if a table of values is representing if I wanted to figure out if a table of values is representing a linear or an exponential growth, what I'm going to do is take a look at the values that are given. That's supposed to be a y there. That totally looks like an x. All right. So we got 0, 1, 2, 3, and we got 6, 9, 12, and 15. So is there a common ratio between these? Nope, we are just adding 3 each time. So this is not an exponential equation, exponential growth. So, let's see. What if we did? All right. We've got 1, 2, 3, 4, 2, 8, 32, and 28. So, what are we doing each time here? So each time we are multiplying by 4, right? However, if we were to put this, so we're multiplying by 4, if we were to do 4 to the x power, all right, so 4 to the first power should be 4. It's not going to give us 2, right? 4 to the second power is going to equal 16, not 8. So that doesn't represent an exponential growth at all as well. So as I'm increasing, so this is a plus 1, plus 1, plus 1. At least on appearance, this is not going to be an exponential growth because of this. Now, sometimes we're going to take so really what we're looking for is there a common difference among the top and a common ratio among the bottom? All right, so common difference among the top is we are adding 1 each time, right? Common ratio along the bottom is we are multiplying by 4 each time. Now, like I just showed you, these don't quite equal out, but what if we had a multiplier in front of our exponential part? So we got 4 to the first is equal to 4, 4 to the second is equal to 16. Is there a number that we could multiply both these numbers by to get the respective values that are in our table? So what can we multiply 4 by to get to 2? And what can we multiply 16 by to get to 8? If we multiplied both by 1/2, then that would work. And if we did 4 to the third power, that's going to give us 64. Multiply that by 1/2, we get 32. So our equation here is going to be 1/2 times 4 to the x power. So an exponential function here is going to be a number or a set of values that has a common difference on top. So we're looking for the common difference in our x values. And a common ratio on the bottom. All right. So anytime we see that, that would be an exponential function. But remember there has to be an exponent. So something like 7x plus 3, this is not an exponential. Okay. Now let's solve for some of these. So let's say we wanted to solve a one variable equation involving the exponents. All right. I'm going to switch back to blue. I like that a little bit better. So to start out, let's do 4 to the x power is equal to 3/2 x plus 5. So in order to do this, one thing we could do is um, we would want to set each of these as their own function. So y is equal to 4 to the x power, and y is equal to 3/2 x plus 5. Um, when we're doing this, this is when you'd want to use your calculator. So you're going to put these into your y equals button, put these equations in, and then you would hit, I believe it's calc, and then intersect. And what you'd find are the places where our linear line, which is the 3x plus 5, crosses our exponential function. And those are going to be your solutions. So we're going to go over this in class. I'll probably make another video on it explaining it a little bit better. But I wanted to give you guys a brief introduction on how to identify exponential growth, exponential decays, and then if you wanted to graph it, all you're going to do is take these table sets of values and put it into a graph. Let's say all you have is a function like 3 to the x power. You're going to pick some numbers. I like to choose one negative, so maybe 3 to the second power, and then what's it going to be when x is 0, and then a few positives, so like maybe 2 and 3 if you wanted to. And then what you do is solve for this, so you would get um, 1 over 3 squared, so 1 over 9. Then you're going to get 1, 9, 27, and then so you'd graph each of these points. So you get your x and your y values. So that's what you do for exponential growth, exponential decay, and we will touch on this a little bit more going forward. Thanks.